Hello, my name's Gary Pocock and this is my week 6 reflection for the E&M modelling instruction course. This week I'm going to reflect on the activities that we did during the week, the worksheet 3 and the PhET potential activity, and finally I'm just going to have some reflection on the origins of the concept of potential and potential energy. Alright, first of all, worksheet 3. So, here we go. So I found this an extremely useful worksheet. I really like the idea of charges far apart and close together and distinguishing them in terms of potential. My immediate thought was to apply energy bar charts to this situation, which I've done in this diagram, and I think this really brings home the system surroundings distinction and the idea that work is being done on the system from the outside, and so the energy in the system, potential energy within the system, is increasing or decreasing in the opposite. It goes in the opposite direction over here. The other point I thought I should mention is that we should be emphasizing that where the potential energy is and that it is stored in the field. I think that should be a constant reminder all the time through this material. The other thing I really liked about this worksheet was questions 8, 9 and 10, the ones with the 4 charges in a square, where you're asked to calculate the net field and also the net potential. I thought that did an excellent job at drawing out the distinction between the vector concept of a field and the scalar concept of a potential. What I did here, I think this should be included in the worksheet, is actually leave a space for 2 diagrams to allow students to draw one diagram with the components of the field in it, and then to draw a separate diagram with the net field in it. I think that would be a lot clearer by including that intermediate step. And I suggested a couple of follow-up questions here, just to so that students can understand the implications of having a zero field and non-zero potential and vice versa. What does that mean? So imagining a test charge being placed at the point P and then asking some questions. How would it move? Alright, so the student would need to recognize that this is a question in which they have to look at the field vector and then discuss the potential energy of the object as it moves away from point P. What's it going to do? Is it going to go up? Is it going to go down? Now, the other thing that I started reflecting on by doing this worksheet was multiple representations of the field. I thought it would really help the students if they could see what the field actually looks like, so that they could go to the eField software and plot the field and plot the potential lines. And so I went and explored this in the eField software, and here I've got the 4 positive charges and field lines and potential lines. Unfortunately, it seems to be a little bit of a weakness of the eField software that the potential lines don't come out in strong detail in the center. We clearly see how as you get further away, this reduces, the potentials become more like those for a single charge, but we'd really like to see more detail in here. So I thought, alright, let's see what the PhET simulation does. So that's plotting potential lines for the 4 positive charges in the PhET simulation. It's a bit more tedious because you have to click and create each field line separately. But you can get more detail for what's happening with the potential lines in the PhET simulation. So I thought that was nice. So overall, it seems to me that the PhET software is better at producing clear lines of potential However, by contrast, I much prefer the continuous field lines in the eField software to the field vectors in the PhET software. So there are the field vectors. So I was reflecting on those field vectors as well while I was playing with this software. I understand what they're doing, and I appreciate the idea of using shading to represent the strength of the field. But field vectors like this, I don't know, they don't work for me. I can't see the patterns very clearly. I don't mind them if they're just in an isolated area, if you're just studying a particular interaction between two charges and you're drawing some localized field vectors. But a full mapping like this, maybe it's just me, but I do prefer seeing the full field lines. But it set me thinking, the use of shading in PhET, why can't we use shading with field lines? So I played around with a bit and did something like that. And so that is superimposing some shading, which I did in some software called, it's a free version of Adobe Illustrator. And it took me a ridiculously long time to do, so I wouldn't recommend it. But I think it would be a really helpful thing to have this shading superimposed on the field lines. Of course, we know that the field line density represents the strength of the field, but to reinforce that with a shading, and furthermore to reinforce the fact that the field is everywhere, not just on the field lines, I think shading would be really helpful. So someone with some better IT skills than I have, it'd be great if they could write a program so that they could have shading at the back of field lines. Alright, moving along, the second activity is the PhET activity. I don't have a lot to say about that. I thought the software was really, the program was really good. The only thing I'd like to comment on is the negative potentials. I thought that was really good, to be able to contrast what's happening with a positive charge in the center and how the potentials are decreasing and going to zero out at infinity, to having a negative charge in the center, where it's still zero at infinity and the potential continues to decrease. I remember when I first learnt this material, negative potentials confused me a lot, so any kind of visualization like this has got to be helpful for learning negative potentials. Again, in the spirit of multiple representations, I think this could be combined with, say, a 3D plot, an Excel plot, or in Plotly, so the students can compare that representation with the 3D representation. In fact, I was imagining a worksheet question where, say, you're given this kind of representation and the students have to match it up with an appropriate 3D plot. Alright, that's the main point I had to say about that. Now, the last bit I'd like to reflect on is the concepts of potential and potential energy. What triggered this thought off was a question in our last session. And someone just said, oh, who was the first to use the concept of potential, or use the term potential? And I thought that was a good question, and I didn't know what the answer was, so I went and did a little bit of research on it, and I came up with these two papers, and I would highly recommend both of these papers. This guy Roche has written really interesting historical reflections on the concept of potential and potential energy, which I think are very insightful and also very compatible with modeling instruction. I won't have time to go through both of them, but I thought I would just look briefly at this paper here. Okay, what is potential energy? Published in 2003. And we learn in this paper that it was Thomson and Rankine who together developed the concept of potential energy and introduced the concept of potential energy. It appears that Thomson introduced it first, but Rankine was the first to explicitly use the term in print. Interestingly, though, there's a couple of distinctions floating around at the time. So this is the middle of the 19th century. Thomson was using the terms dynamical energy, which later he changed the term to kinetic energy, and he was contrasting that with statical energy. Then Rankine took up the idea and introduced his own distinction between potential energy and actual energy. And so we can see here the origin of potential in the everyday sense, which still causes so much confusion to students. But this idea of potential energy as not actual energy was taken up with great enthusiasm in the 19th century. And Rankine says he got the idea from Aristotle. Roche, the author of this article, argues that there are other precedents, and he goes through the complicated history of the term potential, which actually was in existence before potential energy came up. I might save that discussion for another reflection because it's quite complicated. But I'll just say here that it was introduced purely as a mathematical device by Laplace and Lagrange, and then George Green and Carl Gauss independently used the word potential to describe this mathematical function. Yet neither of them explained why they chose that term. Okay, so we even see Maxwell enthusiastically embracing the idea that potential energy is undeveloped energy. So there was quite a struggle in the late 19th century to get clear on this concept. And of course, by not allowing potential energy to be actual energy, as Mark and others pointed out, this meant that the so-called principle of conservation of energy didn't hold. And so we have Mark in 1870 describing the principle of conservation of energy as a convenient housekeeping principle. So it wasn't until later on that potential energy became elevated to a genuine form of energy. And I'm just not quite sure when that was done. Looks like it happened in the 20th century. So just scrolling to the end here. Alright, so reflections on pedagogy of potential energy. Now, throughout this article, Roche contrasts the traditional concept of potential as not actual with the alternative interpretation, which is potential energy is configuration energy. So he used the term configuration energy all the way through this article. And right in the very last paragraph, he says, well, actually, I think that a better term than configuration energy would be Coulomb interaction energy and gravitational interaction energy. And that is something that I would have to agree with. So in summary, what I found really interesting about this paper was how the struggle to clarify this concept in the 19th century is still reflected in the confusions that we suffer from nowadays because of the use of the word potential. And so understanding a little of the history of concepts, I think, really helps, or can really help, a teacher in clarifying those concepts for the student. And the last little point to make is that it's interesting how Thomson made this distinction between dynamical and statical, and then Rankine came along and made the potential and actual distinction, and yet we lost the statical. So we now just have kinetic and we have potential, so we've got a bit of a mismatch happening in these concepts, and that's what we've inherited.